Hello and welcome to this online course on fundamentals of composites and cellular materials. So, for the last few classes we are discussing on a particular topic which is interface in composite materials. So, we have discussed about the basic concept of interface, we have discussed about wettability, we have discussed about interfacial bonding, we have discussed how to measure interfacial strength. Okay. We also discussed about what kind of different kind of bondings in from the at the interface what we see in composite materials. And then from the last class I started talking about certain case studies which actually gives a fairly good idea about interface in composite materials, like in practical applications or in practical examples, how exactly is the interface in composite materials and how does that help in improving mechanical property. That is what we are discussing in these different case studies. So, in today's class also I will continue with that. So, in today's class I have selected two different composite materials. One is metal matrix, other one is ceramic matrix. In the metal matrix composite, it is aluminum matrix, metal matrix composite, where there are three different reinforcement particles, as you can see before C, SiC and Al2O3. And in these reinforcement particles, when we have these reinforcements in the aluminum matrix, how is the interface in the different cases, that is what we will discuss today, we will try to understand today. And in the second example, we will talk about SiC ceramic matrix composite. That means, the matrix is primarily SiC and that is reinforced with SiC fiber as well as SiC particles, and what kind of interface we see there, and as we and in this particular example also the fiber which has been used, SiC fiber, those will be also those also have come from different sources, different kind of fibers, both SiC fibers, but the synthesis techniques are different and that is why their properties are different. So, when we have same material with certain differences in their properties, and this kind of materials when they are used as reinforcement, what is their effect at the interface, and ultimately because of the difference in interface, how that translates into the mechanical property of those composite materials. I think this will be quite interesting to discuss today, as we move on. So, let us start. So, the first example, as I was mentioning earlier, is a metal matrix composite, aluminum matrix, and here three different kinds of reinforcement particles have been used. As you can see before C, that is boron carbide, SiC, Al2O3. All these three particles, all these three reinforcements are heavily used to reinforce metal matrix. Okay. And so, you can see here the to basically to avoid any kind of complicacy from alloying elements, pure aluminum has been chosen as the matrix, and then you can see there are three different reinforcement particles, SiC, Al2O3 and before C, all are in the same size range. Now, before using them as reinforcement particles, they have been preheated. Why this preheat treatment is required? So, that if there is any moisture or if there is any volatile contamination on the surface of the particles, those gets removed, okay, and the surface basically gets active. So, any kind of gas, moisture or volatile contaminants which could be residing on the surface of these particles, they gets removed by this preheat treatment and the surface becomes more active towards towards making good interfacial bonding with the matrix. So, that is the basically matrix and reinforcement, and how this composite has been fabricated. Now, you can see here primarily it has been made by star casting. Okay. Now, star casting, I hope you all remember, it is basically a casting technique I have discussed already while discussing synthesis of metal matrix composite. It is a casting technique, but the casting technique is augmented with a stirrer. Okay. So, that there will be homogeneous distribution of the lower density, most cases it is lower density reinforcement particles, which tends to float at the top or which tends to segregate during the starring. Okay. So, there has to be homogeneously distributed, those particles of different densities from the matrix should be homogeneously distributed in the matrix, and that is why this starring comes into picture. So, ultimately this has been made by star casting, and then after star casting it has been hot extruded. Okay. All these three composite materials, it has been made by star casting and then hot extruded. Now, why do you need hot extrusion? Obviously, to the first reason is that if there is some entrapped porosities during the star casting, those needs to be removed. Hot extrusion obviously helps in that. So, further densification takes place first. Second, it also helps to some extent to basically distribute the particles homogeneously. There will be some cases where there will be agglomeration of particles in some locations. If you are going for hot working, some kind of hot working technique, like in this case hot extrusion, then actually those particles gets distributed homogeneously in better manner. So, the idea of doing hot extrusion is to remove porosity and to get or to maximize the distribution of the particles in terms of homogenization. And then after doing that hot extrusion, heat treatment of this composite material was done again to remove any kind of extrusion defect. Extrusion leads to extrusion means there will be obviously mechanical deformation. Okay. Though it is done at an elevated temperature, it is hot extrusion, but still there could be some kind of uneven extrusion or uneven deformation at certain points, and that would lead to difference in grain size or difference in distribution of particles. To basically get rid of that, this heat treatment, the final heat treatment is done. Okay. So, the particles are mixed together, this matrix reinforcement particles are actually heat treated first, and then ultimately the composite material has been star casted, and then after star casting it is hot extruded. After hot extrusion it has been heat treated further to improve the properties. Okay. Now, you can see here there are different kinds of volume fractions of particles have been taken and star casted for different time, during particle addition and the after particle addition. So, all that there are different kinds of times, different volume fractions have been considered. Okay. Now, let us look into the results. The first hand information what you are seeing here is basically after doing the heat treatment, after doing star casting and then hot extrusion and then heat treatment, how is the microstructure. So, this first one is showing for SiC particles, aluminum SiC, then aluminum Al2O3 and then aluminum B4C, and in all cases the volume fraction is similar, but you can clearly see here that in these two cases the distribution of particles is not that homogeneous. That means, in case of SiC and in case of Al2O3, the distributions are not as homogeneous as you can see in case of B4C. That is the first thing I am seeing here. Okay. You also can see some amount of entrapped porosities in between those agglomerated particles in the first two cases. In case of B4C, however, those kind of entrapped porosities are not present. Okay. Now, the question comes in your mind, in why in B4C, when you are using B4C as the reinforcement, why the distribution is so good. Now, that is happening because B4C particles would be having some amount of oxide, thin oxide layer of B2O3 intrinsically in all B4C particles. It is very difficult to avoid that oxide formation on B4C particles. And also this preheat treatment was done, if you remember, that also would be leading to some amount of oxide formation, B2O3 formation on B4C layer. Now, when these B4C particles are added in the melt temperature is quite high, in the range of 700 degrees Celsius. Okay. Now, at that high temperature, this B2O3 obviously melts. Melting point of B2O3 is in the range of 450 degrees Celsius, right. So, this thin layer of B2O3 now it melts, and it also captures this B2O3 also, the oxygen from B2O3 also gets transformed into aluminum, and it makes a mixture of B2O3 and Al2O3. Okay. So, it is basically a thin liquid layer of B2O3 that improves the wettability of the B4C particles in the aluminum melt. Okay. This thin layer of B2O3 Al2O3 formation improves the wettability, and because of better wettability there is better distribution. I hope it is clear to all of you that why B4C is showing better distribution, because it shows better wettability. Why better wettability? Because intrinsically B4C would be having some oxide layer, B2O3 layer, which gets molten at that melting temperature of aluminum. Even in case of star casting, you keep the temperature a little higher than melting point. So, obviously, B2O3 melts and it makes a thin liquid layer on the surface of B4C, which improves the wettability, and that is why B4C particles are homogeneously distributed. And after hot extrusion, in all cases actually there will be reduction in porosity, that is not really needed to be mentioned. So, yes, so after hot extrusion a reduction of porosity and a better distribution of particles were achieved in all composites. That is going to happen anyway. Okay. But ultimately B4C shows better wettability. Let us move on, let us go into a little bit more deep. Now, if we look at the interfaces of these three cases, SiC, Al2O3 and B4C all are in aluminum matrix. What we are seeing here, these two interfaces are more or less clean. However, here we are seeing some kind of phase formation or something is happening at SiC-Al interface. Okay. That is what we are seeing. So, let us look into more details of Al-SiC interface. Now, you are seeing here two different starting time has been shown here, one is 27 minutes and other one is 105 minutes. You can see here when the starting time interaction layer time is less, you do not really see any interaction layer. As you move on, as you increase the time of residence time, as it increases, what you see actually, you can see there is a clear layer is forming at the interface. What is this layer? Now, the first thing is that this SiC, okay, again SiC would be having some oxide layer on the surface, and that would actually convert into Al2O3, because of Al when it comes in contact with aluminum melt for longer time, there will be interdiffusion, and that would lead to formation of a thin Al2O3 layer. But then you can see also there is another thicker phase in the range of around 3 micrometer thick phase is also forming as the residence time increases. Now, what phase is this? So, let us look into that. Okay. So, as I mentioned earlier, that preheated SiC particles form a thin layer of SiO2 on the surface, and then once it is in melt, then this oxide layer reacts with the aluminum melt and it could form Al2O3, and that is what you are seeing here, okay, at the interface. But along with Al2O3, you also see a thicker layer which is around 3 micrometer forming at the interface of aluminum and SiC. What could be that? Now, if you look at the reactions, okay, let me just, before I talk about this particular product formation, let me show you again the X-ray mapping result. So, what you are seeing here that is the SiC particle, this is the SiC particle, and then beyond that you have the aluminum matrix, and then in between these two at the interface you see quite a thick interface is here. Okay. So, obviously something is happening here. What I am trying to say is that if you see, so basically I am talking about this layer, as you can see here, this particular layer. Okay. Here also I do not know if it is clear or not, but you can see here there is a layer like this. So, okay, as you can see here, this is a layer like this. Okay. Now, this one, this side is silicon is here. Okay. So, this is silicon particle coming. So, Si is coming from there, okay. And then this is here the aluminum, you can see here this is the aluminum. So, in between this at the interface you can see there is quite thick interface. So, and as you have seen here, in this particular, so as you can see here this particular thickness what is forming. So, the point is that what is that? Again, thermodynamically all kind of things could be happening, like aluminum carbide formation, as you can see here, or this kind of complex carbide like aluminum silicon carbide formation, where this aluminum silicon carbide formation is more feasible, and that is why this layer which is forming, as you can see earlier also. Let me go back once more to the previous slide, and you can see here this particular layer. This is nothing but it is a aluminum silicon carbide combined it is forming by the interdiffusion, and that is why you see this thick layer. And aluminum silicon carbide is a brittle phase, as you all understand, as you all know, and that is why you can see also presence of these cracks also during solidification. During solidification there will be residual stress generation, and that residual stress will actually lead to crack formation in this brittle phase. So, obviously, this kind of phase formation is not wanted, not welcome. All right. So, now if you look at the other two cases, like in case of Al2O3, where Al2O3, obviously there is no reaction product formation, but then we will see something else there later. If we look closely in case of Al4C, earlier we saw that this B2O3, Al2O3 is forming, and then if you look at the look away from the interface, what we see in the matrix itself, very tiny particles of Al2O3s are distributed, and that is basically coming from the interface of AlSiC, where SiO2 first formed, and then from there Al2O3 formed. Those Al2O3 particles are actually getting detached, tiny nanoparticles are getting distributed all over the matrix. Those are not remaining at the interface to that much. Okay. Second thing also we are seeing that this kind of Al3BC, okay, large particles are also forming, but again these are away from interface. So, in the interface in case of B4C is quite clean. This Al2O3 or this Al3BC, these are not really harmful if they are actually present in the matrix distributed well. Okay. So, that is what we are seeing here, that no clear interaction layer at the interface in case of Al4C, and the two secondary phases what we are seeing here, these are actually away from the interface, and these phases are not detrimental in terms of mechanical properties. So, the next thing obviously we would like to see at the fractured surface. So, the fractured surface images have been shown here, and you can see this is the first one is for SiC, second one is for Al2O3, and third one is for B4C reinforcement. Now, you can see here in case of SiC, you can clearly see there are a lot of cracks. Okay. You can see here also there is crack, okay, and these cracks are mostly in between these SiC particles. Okay. Clearly you can see here, okay, and these cracks are basically coming from that if you remember earlier, this phase was forming at the interface, this phase is forming, which is basically this Al4 SiC4, and that leads to crack like formation like this. Okay. You can see here this crack, here also cracks, everywhere there are a lot of cracks. Okay. In case of Al2O3, what you see here, the interface itself is not very tightly bounded, or weakly bonding you see at the interface between Al and Al2O3. The interface is clean, we are not seeing really formation of any other products, but interface itself is quite weak as it is. Okay, you can see here the cracks are getting generated at the interfaces. However, if you look at the B4C reinforced aluminum matrix, you can clearly see there is not really much cracks anything. Okay. You can see here nice ductile fracture, you can see this cleavage fracture, okay. But you do not really see any kind of crack or interfacial delamination in case of AlB4C. So, clearly AlB4C stands out if you compare the three different reinforcements here. Okay. AlB4C system shows the strongest bonding as revealed by good matrix particle adherence, no gap or micro void at particle matrix interface. Okay. AlSiC weaker bonding than AlB4C, relatively low adherence, and in case of Al2O3 it is the weakest bonding. So, ultimately what we get from here is that in case of AlB4C it is the best particle distribution, better interfacial bonding, well distributed, non-detrimental secondary phases away from interface, which in fact can improve the mechanical property to some extent. In case of AlSiC, the interface is clear. Okay. However, there is actually a interfacial reaction layer is also forming, okay, which is Al2O3 and Al4SiC4. Okay. And then AlB4C and Al2O3 they do not have any reaction product formation, but in case of Al2O3 the interface itself is weaker. Okay. That is why it shows low adherence. Okay. So, that is what actually we are learning from here, that what kind of reinforcement we should use and what kind of reaction could be taking place at the interface. So, this is one nice example which actually teaches us that how should we how should we look at interface, how should we characterize interface, what are the things we should look for when we try to characterize or when we try to understand interface in a metal matrix composite material. All right. So, with that let us go to the next one, next example. In this example, what I have considered is a ceramic matrix composite. That means, the matrix is ceramic, SiC in particular, and that has been reinforced with SiC itself. So, what is there? In this case, obviously, this particular SiC, it actually this particular example I have taken from NASA. So, this application is gas turbine engine combustion liners, okay, high temperature applications, okay, where SiC composites are used, and the matrix actually is basically SiC matrix, where silicon melt has been infiltrated in SiC. Okay. So, I will give you the details of how it has been made, then it will be more clear to you, and the reinforcement is SiC fiber only, but they have used two different kinds of SiC coming from two different sources, high Nickelon and ceramic. Now, do you remember the term Nickelon? Can you remember? I have mentioned it earlier, this term Nickelon. Yes, Nickelon is a SiC fiber. How it is made? You remember? It is made by the technique. What technique is that? Polymer pyrolysis. If you remember, it is polymer pyrolysis. Okay. Both this high Nickelon and ceramic both have been made by two different companies, okay, two different vendors. One is Nickelon, other one is ceramic. The difference, there is a subtle difference between these two. Both are made by polymer pyrolysis, but high Nickelon is having little bit of higher carbon. High carbon content is there, little bit high. It is not. So, SiC should be in stoichiometric. Ideally, it should be stoichiometric composition. So, SiC, it should be SiC, but then how you make it. If you remember, I talked about in case of CVD synthesis, there actually you can actually change the hydrogen concentration. Hydrogen is used as what do you call it, catalyst in making SiC fiber. So, you can change the concentration of SiC. We have discussed in details about that, and that would actually change the stoichiometry from high carbon to high silicon. Okay. So, here actually carbon content is a little bit higher. So, it is called high nickelon, and ceramic is actually almost stoichiometric. It is more towards stoichiometric. In both cases, both actually having low content of oxygen, which is good, okay, because during polymer pyrolysis, okay, you have to get rid of those other elements. Okay. So, yes, oxygen actually is used. I mean, there is a step during polymer pyrolysis which is stabilization, which is basically oxygen ions, oxygen atoms gets attached with the structure, and that ultimately finally gets removed also. Now, the aim during SiC synthesis would be by polymer pyrolysis would be to get rid of the complete oxygen atoms towards improving the mechanical properties. So, in both cases the oxygen content is low, but in one case it is high carbon, in other case it is more stoichiometric. Okay. Now, let us see how this composite has been made. Okay. So, this is something we need to understand, is that this kind of SiC fiber has been taken, okay, which is basically woven fiber, 2-dimensional woven SiC fiber preform has been taken, and then on this fiber there is an interfacial coating has been applied of boron nitride by CVI, chemical vapor infiltration. So, you can consider, let us say this is, let us take this area, sorry, let us take this area and let us zoom it and let us look at one fiber. Okay. So, let us say this is the SiC fiber, and on top of that, as you can see here, a thin layer of boron nitride has been deposited. So, this is boron nitride, and this has been deposited by chemical vapor infiltration, and then on top of this boron nitride there is another layer has been given of SiC, both by chemical vapor infiltration, and this has been done to make the structure, make this this mesh structure, this woven structure, to make it more rigid. Okay. This boron nitride and then SiC has been deposited, thin film by chemical vapor infiltration, and then what has been done, initially a slurry of silicon has been made. So, you can see here has been mentioned here. Okay, you can see here, yes. So, you can see this SiC particulate slurry has been made, and then in this large pores, these SiC particles, the slurry goes in. So, this SiC goes in, and after doing that thing, this the whatever porosity is remaining, those small porosities or micro porosities what are remaining, those gets infiltrated by another phase, which is silicon, molten silicon. So, molten silicon gets infiltrated in the remaining porosities. So, initially you take SiC mat, as you can see here, this SiC mat has been taken, and then on top of that boron nitride and SiC gets deposited, thin film of those gets deposited by chemical vapor infiltration, and just to make the structure rigid, and then those porosities, large porosities gets filled with SiC particulates, and then whatever porosities are remaining, those gets filled with silicon melt. Okay. Silicon gets solidified, and then ultimately you get a composite structure, where it is SiC fiber, matrix is also SiC to some extent, and then the rest remaining is Si. Okay. So, now let us look into the, so now I think we understand how the composite material has been made. Our aim in this particular study would be to understand the difference between high nickelon and ceramic. We have used two different kind of fibers. So, the aim would be to understand, if we use these two different kind of fibers, what kind of changes in properties we will be seeing. So, let us go into that. The first image what we are seeing here are basically fractured surface of tensile test samples, and this tensile test has been done at higher temperature 1200 degrees Celsius. So, all this mechanical testing on these samples will be seen done at higher temperature, because we are looking for high temperature applications. Okay. So, high temperature tensile test 1200 at 1200 degrees Celsius temperature tensile test was carried out on the composite materials, and you are seeing the fractured surface. What you see initially, it is clear that this surface is much more rough compared to this. If you look closely, actually here you can look closely, you see the long fiber. So, this side is for Nickelon, this side is for ceramic fiber. So, here reinforcement is Nickelon fiber, in this side the reinforcement is what do you call it, ceramic fiber. Okay. Now, what you are seeing here, that the surface is much more rough here compared to this, and at higher magnification you can see there is long fibers coming out, okay, where the fiber length which has come out is less. That means, from here, that is how actually you have to judge, you have to characterize the fractured surface in composite materials. So, what is the difference here? Only the fiber length. So, from there what we can deduce? We can say that the fiber pull out mechanism is more pronounced in this case, is not it? The amount of fiber pull out is more here. Okay. So, in both cases, at this particular temperature when the UTS was done, in both cases the strength is similar. However, the strain to failure is high in high Nickelon case. You can clearly see here, because of higher amount of fiber pull out, okay, the amount of, the failure strain or strain to failure is also high, in fact almost double. Let me give you the data. So, you can see here that in both cases the tensile strengths are almost similar, around 286 MPa. Okay. However, the strain to failure in case of high Nickelon is around 0.48, whereas in case of ceramic fiber it is 0.21% only. Okay. So, it is almost double. In case of high Nickelon fiber, it is almost double than the ceramic fiber. Okay. That means, there is more pull out, more strain to failure, and because of that, the important point is that fracture toughness is high in case of when you are using Nickelon fiber compared to this ceramic fiber. Okay. Now, why is that? That question should be coming in your mind. Why is that? This is actually because there are two reasons. One is that because of the better stoichiometry of ceramic fiber, they have better modulus, higher modulus. Okay. So, when you have higher Young modulus, obviously strain would be little lower. Not only that, if you look at the surface of these two fibers, this is for Nickelon and this is for ceramic, you can see ceramic fiber is having certain amount of roughness, and this roughness is actually improving the interfacial bonding, and because of that the amount of pull out is less, and that is why you saw that the strain to failure is less in case of ceramic fiber, and that leads to lower fracture toughness. However, though it shows lower fracture toughness, but because of higher modulus and because of some other reason which I will explain, this high Nickelon fiber shows poor fatigue resistance. In other way, the ceramic fibers shows better fatigue resistance at higher temperature. Both have been done here, I think at 1200 degrees Celsius. Okay. And here you can see what you see here, the fatigue resistance actually. So, you can see the number of cycles, okay, 19 cycles and here 501 cycles. Okay. You can see the time also 38 hours, here is 1002 hours. That means, clearly the fatigue resistance is better in case of ceramic fiber. So, one reason obviously you can tell that the modulus is higher, little higher in case of ceramic fiber because of better stoichiometry, and that obviously would lead to better fatigue resistance, but that is not all. What is happening actually, there will be a glassy silica layer formation in between. So, if you remember, there was a boron nitride coating was made on the SiC fiber, okay, and there is a glassy glassy silica layer formation at that case. Let me show you the TEM images. I think that will be, it will be giving you better information. So, if you look here, initially, before doing the test and before, I mean, basically initially as processed composite. So, you can see here this is the boron nitride layer, and then you have this side, you have the silicon carbide fiber. In between that, you can see there is a carbon rich interlayer, and this carbon rich interlayer is coming because you have used high nickel fiber, mean it is already having some amount of higher amount of carbon, and that carbon actually is getting reflected here. Okay. So, the interface of boron nitride coating and SiC fiber, there is a thin layer of carbon. When you are doing the test at higher temperature, this carbon gets oxidized, and some amount of, so that goes out, and some amount of silicon from silicon carbide also gets oxidized, and that forms an amorphous or glassy layer in between the boron nitride layer. This is the boron nitride layer, and this side I think we have the SiC fiber. So, in between this layer, which was earlier carbon layer, okay, that carbon rich layer, that gets converted into SiO2 layer, which is amorphous or glassy, which is brittle in nature. Okay. Because of this SiO2 layer formation, silica layer formation, glassy silica layer formation, we have seen here that the fatigue resistance goes down in case of nickelon. So, nickelon, though it shows better what do you call it, better strain to fracture or better fracture toughness, but then fatigue resistance at higher temperature is poor if you compare with the ceramic fiber. Okay. So, that is what has been mentioned here, that ceramic crystalline stoichiometric SiC, ceramic is crystalline and more stoichiometric, was found to exhibit improved thermal and environmental stability than the carbon rich high nickelon fiber. The instability of the high nickelon was related to formation of a thin carbon rich interfacial layer between the fiber and the boron nitride fiber coating during the composite fabrication, as I have discussed just few minutes back. As you can see here also, this carbon rich layer, and this carbon rich layer you can see on subsequent exposure in oxidizing environment under stress, this carbon rich layer converts into glassy silica layer. Okay. And that is why initially you have seen the strain to failure for high nickelon fiber is quite higher. So, the fracture toughness is higher, and that is coming from the surface roughness of ceramic fiber and higher modulus of ceramic fiber. That leads to better interfacial bonding and less failure to strain, less strain to failure. Okay. And ultimately, because of this glassy layer formation at the interface of boron nitride and silicon carbide layer, in case of high nickelon fiber shows poor high temperature fatigue resistance compared to the ceramic fiber reinforced composite. All right. So, in this class we have discussed two different kind of composite material. One is metal matrix, other one is ceramic matrix. In metal matrix, there were three different kind of reinforcement particles, and we discussed what kind of interface forms in these three different kind of reinforcement in these three cases, and how those interfaces actually affect the mechanical property or could affect the mechanical property, that we discussed. And then the second case, it was purely silicon carbide matrix, silicon carbide reinforcement. It is basically ceramic matrix 5 composite, okay, and the whole thing has been basically glued together by silicon melt. Okay. So, silicon melt's role is basically to hold together everything, and some amount of silicon gets converted into SiC and SiO2 also. But what you observe, in this case there are two different kinds of what you call it fibers were used, and based on the natures and properties of these fibers, the composite materials fatigue resistance and tensile strength varies. Okay. That is what we observed. So, in the next class we will also continue with some more case studies, and then once we complete this class, then we will go into mechanics part of composite material. Okay. With that, I would like to conclude today. Thank you all.